Okay, so today we're going to finish talking about isolated singularities. Right, so isolated singularities. So remember what the setting is, right? You have a function, and you have the function is analytic. In some ball around the point, right? You have some disk around, and it's analytic in that disk, except maybe at the center, right? And so the center point is called, an isolated singularity, and so in other words, has an isolated singularity there. Right, and in that case, you have a Laurent expansion. So has a Laurent expansion. Laurent expansion, right? And then there are three kinds of singularities, basically, right? One, it could be a removable singularity. So if a sub n is equal to 0 for all n less than 0, then we call this thing a removable singularity, right? Call z naught a removable singularity. If a finite number of the negative terms are non-zero, then you say it has a pole, right? So if a minus k is non-zero, so k some natural number. If a to the minus k is non-zero, and everything preceding it, and a sub n equals 0 for all n less than negative k, then we call z naught a pole of order k, right? And then the third type of singularity is if an is non-zero for infinitely many negative integers. Infinitely many negative integers, in that case you call z is called an essential singularity. So three kinds of singularities, and today we'll be talking about each kind in turn, and the behavior of the function. It turns out that the behavior near these types of singularities is quite different. Okay, particularly the behavior near an essential singularity and the behavior near a pole is radically different. So just to give you some concrete example of this, if you look at sin z over z, right? Then the Laurent series, so this has an isolated singularity. At 0, right? It's a singularity at 0. It's not defined at 0. It has the Laurent series 1 over z times the power series for sine. Right? So sine z minus z cubed. 3 factorial plus z to the 5th to the 5 factorial minus 7. Right? And so you see that its Laurent series looks like this. Right? This is its Laurent series, and you see that you have a removable singularity. right? So there are no negative terms here, right? You can define this thing on the right defines an analytic function on the whole plane, right? And so you can remove the singularity by defining the function to be 1 at 0, right? So you have so this is a removable singularity. Right. If we considered, say, sine z over z cubed, right? Then what does that have at 0?
A pole.
You'd have a pole of order 2, right? Because you're going to have 1 over z squared minus 1 over 3 factorial plus z squared over 5 factorial minus all etc. Right? And so it's got a pole, right? It clearly has a pole there of order 2, right? And if you look at say sine of 1 over z, right? Then that's going to be 1 over z minus 1 over 3 factorial z cubed plus 1 over 5 factorial z to the 5th minus 5 factorial. And you see that this thing has an essential singularity at 0. Okay. So just to give you some concrete examples. Okay. Everything that I put on the board is in the notes, so I don't know why you're copying it all down, but go ahead. I guess some students have said that it helps them to remember it to copy it down. So, yeah. But I should say that the classmate of mine who impressed me the most when I was an undergraduate, I got to Princeton and looked around, and there are all these really, really smart guys, right? And the guy who seemed to me the smartest was this guy who sort of sat around like this. And he spoke with a lisp. He's like, and it was just this sort of like easygoing guy. Mm-hmm. And he never took any notes. I'd watch him, he'd just like write down a couple words here, write down a couple words there. I wish I could be like that guy. But and now he's a very, very strong mathematician. And that's what you should shoot for. This guy who didn't take down any notes, but just thought.
The problem is that's great when you can focus,
yeah.
And then if the writing forces you to focus.
Yeah.
So for me, it is the most effective, but I have to be not tired and I have to be fully engaged.
Yeah.
Otherwise I'll lose track.
Yeah.
So.
Yeah. Okay, so removable. First, we're going to talk about removable singularities. And remember, we started talking about it by recalling a corollary from lecture 11 that isn't in the book, but it's sort of a cool way to approach cool way to approach these. So we have this corollary. Suppose F is analytic. This is back from lecture 11, as I said. Analytic in a region omega prime obtained by omitting a point A from a region omega. An analytic function on omega that agrees with f on omega prime exists if and only if the limit of z minus a f of c equals a is 0. Okay, that's what we sort of started off with last time. Right? So it's like I said last time, it's basically saying that you have it's a condition for the existence of removable singularities, right? A removable singularity exists if and only if this happens. Actually, this is in the book, but it's only introduced at this point. And I think the proof is given in a different way. Okay. Just for fun, let me introduce let's go on a small digression, okay, which is the connection with the Taylor expansion. So connection with a Taylor expansion. That you can actually get sort of a limited version of the Taylor expansion from this above observation. Okay. So here's the theorem. You don't get the full-blown Taylor expansion, but you get something which you could call a finite Taylor expansion. Okay. Say f is analytic on omega, and let A be a point in omega. Then f of z can be expressed as summation k derivative at A over k factorial z minus A to k equals 0 and minus 1 plus s of n z minus A to B. So you know this already, actually, right? I'm sorry, where f sub n is analytic on omega. Okay, so this first part, is the first n, the first n parts of the Taylor expansion, and then you have z minus a to the n times an analytic function. Okay, so this is an immediate consequence of the infinite Taylor expansion theorem, right? Once you have the infinite Taylor expansion theorem, certainly you have the finite Taylor expansion theorem immediately. Okay, so it's sort of maybe not that impressive to introduce it at this point, but let's see how you can get it. There's a cool sort of a tricky way that you can get this thing from the above observation. Okay, and I think I just thought maybe you'd like it. Okay, so here's the proof. Apply the corollary to the function f of z minus f of a over z minus a. Apply the corollary to this function, right? This function, you notice that if we multiply it by z minus a and take the limit as z goes to a, you get 0. Right? So certainly the corollary applies to it. And notice that the limit as z goes to a of f of z is f prime a. So what do you get? You get that there exists an analytic function f1, right? So that f1 equals f of z, big F of z, when z is not equal to a, and equals f prime a at z equals a. Right? That's just the consequence of the corollary. Okay. Okay, and then what we do is iterate. You say, well, okay, let's do exactly the same thing for f1z, right? Let's apply the corollary to f1z minus f1a over z minus a. What you get is one obtains another function f2z, which equals f1z minus f1a over z minus a, because z is not equal to a, and f1 prime a over z equals a. And you keep on going. Okay. So you say that, what happens? What can you get out of this? Thus, what you obtain is the following. You get that f of z is f of a plus, like this, z minus a f1a, f1z, excuse me. Right. F1z is equal to this. And then you just multiply through, and you get this equation, right? And you notice that this is valid not just for z not equal to a, but also z equal a also. Right? Because when z equals a, all you're saying is that f of a equals f of a. So this is true for all z. You get this. Right? So now f1z, similarly, f1z is going to be f1a plus z minus a f2z, and so on and so forth. Okay. Now you see, like, if you substitute f1z, substitute this thing in for f1z, what you get is f of z equals f of a plus z minus a f1z, right? So it's going to be f1a plus z minus a squared f2z. Right? And you see what's going to happen, right? You also have a term for f2z, you substitute in, and so ultimately you get f of z is equal to f of a plus z minus a f1a plus z minus a to the n f sub n z, right? Where this f sub n z is an analytic function. Right? Okay. Right? And that is your excluding that last term, this thing is your Taylor expansion. Right? This thing is your Taylor expansion because you see that the kth derivative of z, the kth derivative of f evaluated at a is going to be k factorial f sub k a. Right, and so f sub ka is of course over k factorial. And so putting that back in gives you the Taylor the nth Taylor polynomial plus z minus a to the n times this analytic term. So this is a sort of clever way of obtaining a finite Taylor expansion, and it tells you something about the remainder term. But I guess it doesn't tell you very much about the remainder term. But if you hold on 1 second, you can see you can get a little bit more. Okay. So any questions about the first part of this, of the finite Taylor expansion? So all we did was just, apply this thing iteratively, and this it happens to give us this sort of information. In fact, maybe I should call this part 2. So I'll call this part 1, part 2. In fact. FMZ, you can you can calculate what f and z has to be. F and z is going to be, one can obtain an integral formula for that remainder term, where C is any circle about A, such that C and its inside are in omega, and Z is inside C. So in fact, one can obtain an expression for the remainder term. Okay. Without much difficulty. So here I'll just sketch it. Say, okay, well, I know that I have an integral form for. I guess maybe it's obvious what we're going to do. We're going to use Cauchy's integral formula to obtain an integral form. Okay. So right, we want to get some expression, expressing f and z as an integral. Here's an obvious one. No, it's not that interesting. But, Cauchy's integral formula. Okay. At this point, you say, well, look. In the previous, I have this expression for fn. Right? I know that in the above, that z minus a to the n fn z is this thing f of z minus summation minus the Taylor polynomial. So dividing both sides by this thing, I see that what you see is that z is 1 over 2 pi times fn. Well, fn is f of z minus the polynomial everything divided by z minus a to the n. And I also have a zeta minus. Nope. What am I doing? These should all be zetas, right? Zetas. I also have a zeta minus z. Right. Okay. So what you see is that right, you basically have the thing that you're looking for. Right. Except you also have this an integral involving things that look like this. Right. So it remains to show that anything of the form d zeta over zeta minus a to the n minus k zeta minus c. That all these things are equal to 0. Right. If you show that these guys are equal to 0, then that's the end. Okay. It's actually not too hard to show that. let me sketch it out. Let me sketch it out. It was pointed out in the comments, as you might have said. Like if you're not going to tell us exactly how to do it, at least sketch it out how you're going to do it, how it should be done. So let me. So one can do this inductively. So it can be done. Basically, it's not exactly that, but let's call this thing f sub. So for k between 1 and n. So I have n minus k, where k ranges between 0 and n minus 1. I'm replacing it by k, where k ranges from 1 to n. That's the same thing. But this k is not the same thing as that k. This k is the n minus k from before. Okay, so how do you do this? For k equals 1, you pull a trick, which is you say, well, d zeta over zeta minus a zeta minus c is the same thing as 1 over z minus a, 1 over zeta minus c, minus 1 over zeta minus a d zeta. You just do an extension. Okay. And what's this? Well, this is the integral of 1 over zeta minus z. Remember what c is, right? C is some circle around A, right? And z is some other point inside C, some other point inside C, right? So what's this? This is going to be 2 pi I, right? Minus, again, 2 pi I, and so you get 0. Okay? So you get 0. Okay. Right? Because you're just you're integrating this loop around this thing. You get 2 pi I. Okay. So what you get is that f1a is equal to 0. And then the second thing to notice is that if we look at fka, that is actually the derivative. If we look at say k plus 1a, that's the same thing as that's this k plus 1 zeta minus c. But what is that? Do you reckon? Does anyone see the relation between these two things? So what's the relation between fk plus 1 and f1? Fk. But zeta, remember, zeta is your variable here, right? Zeta is your variable. Okay. But maybe you remember the integral form of the derivative, right? The Cauchy form for the derivative, right? And you see that what's this? Well, this is the kth derivative of this function, right? This is the kth derivative of the function of this integral. Right. So this is actually, that's not exactly 1 over k factorial, the kth derivative of the above function. But the above function was 0. So that's how you do it. Okay. So that gives you an expression for the remainder term in your Taylor series. Anyway, those just to give you sort of a different point of view of the Taylor formula. Any questions? Any questions? Yeah, question.
So just to clarify, this step right here is just a consequence of the the Cauchy integral formula for derivatives?
That's right. That's right.
Okay.
Right. Okay. 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 So now let's go back to what actually is the topic of today, which is removable singularities and poles and stuff. Remember, we ended last class with this thing called Riemann's theorem. I just find it really fascinating how everybody presents complex analysis from completely different routes. I've got a stack. If you visited my office, you may have noticed there's this large stack of books on it. Those are all complex analysis books. And I'm sort of going through and saying, oh, so they go like this. Maybe that's a more interesting way to present it. It seems like if you go from one book to the next, they take rather different routes. It's great. Then maybe that's you really understand it. You see it from different points of view, rather than just saying, I only know one way of explaining this. Okay. Okay. So Riemann's theorem. Let F be analytic and bounded in some neighborhood, some puncture neighborhood of Z0, then either F is analytic at Z0 or it has a removable singularity there. Okay. So, in other words, if you know it's bounded in some neighborhood, then you know it has an analytic extension. Okay. So either it's already analytic there, or it can be made analytic there. Okay. Okay. So you recall that last time we gave a really short proof of this, which was use the corollary, right? And the corollary says, if the limit as z goes to z0 of f of z is 0, and it certainly is. And it certainly is, then you have a removable singularity in the end. Okay. So that's one way to do it. It's sort of there's another way to do it that's sort of reminiscent of the proof of Cauchy's inequalities. So let's say that f is not analytic. Is not analytic at Z0. Then f has some Laurent expansion. Right, it has the positive part, and it has the principal part. Okay. And what we're hoping to show is that that this part vanishes. Right? We're hoping to show that all the bn are 0. Okay. Okay. So you say, well, let's recall what these b sub n are. Right? The bn are just these integrals f of z over z minus z naught to the negative n plus 1 dz over c rho, right? Where rho is some is the radius. Okay. And so we're hoping to see that that the b sub n's are all 0. Right? So let's just attempt to get some crude bounds. Right? Let's bound the b sub n. Right? Let's bound those guys. Right? So what do you get when you bound this? Right? We know that as long as we're assuming that rho is smaller than epsilon, there's a bound for f. Right? So for rho less than epsilon, we know that f is bounded by some constant f. Okay. So, and further, we know that so this is smaller than 1 over 2 pi integral of n over rho to the negative n plus 1 dz c1. Okay. 2 pi rho over 2 pi m over rho to the negative n plus 1. Right. And so what do you get? You get m rho n. Right. So you see that B sub n is controlled by the bound times the radius of the disk to the nth power, right? And that's remember that this rho can be any rho bigger than 0, right? So you just let the disk shrink. Let the disk shrink, and you see that the B sub n's are all 0. So let rho go down to 0, and then so the B sub n's go to 0, and so they're all equal to 0. I think I like that better. That's more direct and doesn't rely on anything. Well, I guess it relies on the existence of a Laurent expansion. So that's a pretty serious thing. But let's make it more like. Okay, questions? Questions? Yes, Michael.
So I just don't remember why exactly when you have the bounded, how does that imply that it's a removable singularity? Where does that come from? I mean, I understand.
Oh, so
we can prove them.
So I mean,
They're sufficient.
so we're just using the previous corollary, which said that if this limit was 0. Right. If this is 0, then you have a removable singularity.
Yeah.
Okay. Well, if this is bounded, then this limit is going to be 0, right? Because you've got something bounded times something that goes to 0.
Oh, gotcha.
Right.
Okay.
So the product is going to be 0. So that's it.
Thank you.
Other questions? Yeah, Christian.
I'm not clear on how you get this formula for Bn.
That was part of the Laurent expansion.
Okay.
Yeah, that's what you get when you work out the Laurent expansion. Those are the integrals that show. Okay, so what one gets, if you put this all together, is you get a bunch of equivalent things. So F has a removable singularity at Z naught is equivalent to F being bounded in some punctured neighborhood of Z naught. Is equivalent to the limit, this limit being 0. And it's easy enough to slide in another condition that the limit of f of z as z goes to z naught exists. So you get basically a characterization of removable singularities. So we didn't really prove this, but it's just an exercise in logic to slide it in the appropriate place. Okay, so now we're going to talk about poles. I hope we make it to essential singularities, because then we can we'll get to the interesting theorem of Casorati-Weierstrass. I don't know if we'll make it. We'll make it if I go faster. Okay, so first off, we're going to start off with a characterization of simple poles. So characterization of simple poles. In some sense, we don't need to do this, and I'm throwing it in again just because it's another way of doing things, and I think it's interesting. It's not that interesting. Anyway, it's another way of looking at things. So Z0 is a simple pole if and only if the limit of Z minus Z0 times f of Z as Z goes to Z0 exists and is non-zero. In which case, this number, this limit, is the residue of Z0 is a simple pole, is the residue of f at Z0. So, the first part is, the forward direction, right, is pretty clear, right? If you're a simple pole, right, that means that your Lagrange expansion, has some power of 1 over Z minus Z0, right? That's the only negative power term, right? And so, if you multiply that by Z minus Z0 and let Z go to Z0, then you're going to get the residue, right? So that part is just, do you know what a simple pole is? Right? That's just follows from the definition of simple pole. Like, is that clear? Does that make sense? Michael, is it all right?
Yeah.
Okay, good. Okay, and then the backwards direction is sort of clever. You say, well, let's say that the limit of Z minus Z0 is some number that's not equal to 0. Okay. Then, in that case, we're going to look at the limit of Z minus Z0 times Z minus Z0 for Z. Well, I do get 0. Right? Because the limit of this thing is 0. So I've got something that goes to something non-zero, right? Some non-zero finite number times something that goes to 0. And so the product is going to be, the limit of this product is going to be the product of the limits, namely 0 times some number. Okay. So what does that tell you? Right? That tells you that so the limit of this thing, the limit of Z0 times Z minus Z0 times this thing is 0. So what does that tell you, Celis?
Wait, sorry, I have a question.
Yes.
So what if you did the multiplication out?
Yes.
And then you split up the limits using the sum rule, and then you'd have the last term would be a constant. It would be Z0 squared times f of Z0, right? Which is not necessarily 0. Or would it cancel? Would they all cancel?
Don't make things too complicated. Right? You just have, you're looking at the limit of f of something, something times something, where z goes to some point, and you know that b of z goes to a constant, we know that A of z goes to 0, right? So the limit of the product is just going to be the product of the limits, 0. Right? This thing goes to some constant alpha. Right? This thing will tend to alpha. This thing tends to 0, and so you get 0.
Wait, so when are you not allowed to do that rule?
When the limits don't exist. But if the limits exist, then it's perfectly legitimate to say that the limit of a product is the product of the limits. Yeah.
How do you know that the first limit is not infinity?
That's part of the assumption. So suppose this limit exists and is non-zero. And I guess they mean a finite limit. Yeah, maybe it's not completely clear. It is a finite. It is a non-zero finite number. Okay, so what does that tell you? That tells you that this thing has a removable singularity, right? Because using the corollary, right, we know that this z minus z naught times this guy tends to 0, right? So what does that tell you? So by the corollary, we know that z minus z naught after z must equal some right? Must equal some analytic function. Right? But what does that tell you? That tells you that f has a Laurent expansion that starts with the -1 term. Right? So f starts with z minus z naught n minus 1 from 0 to infinity. Right? So it has a Laurent expansion that starts with a -1 term, and so you have z naught as a pole, as a simple pole. Right? And the residue is going to be a 0, namely the value that you get negative this value. So it's, I don't know, it's cute. Okay.
I thought that was cool.
Okay, good. Thank you. You saved me like a comic with a silent crowd. Yeah. Okay. Okay. So in fact, we didn't really need to do that, but one could go a more direct route and use, one has a more general theorem, which is the following. So a more general theorem, which should look kind of familiar to you. So let f be analytic in BR. In some punctured disk, right? So let there be an isolated singularity at z naught, is what I'm saying. F has a pole of order m at z naught, if and only if f of z equals 1 over z minus z naught to the m times theta z. I'm sorry, phi z for some phi, which is analytic and non-zero at z naught. This should look kind of reminiscent of something else, right? What does it remind you of? The same statement for the not for the zeros. Remember, we had the statement that you have a 0 of order m if and only if you are, if and only if you are z minus z naught to the m times some analytic times an analytic function, right? And so this is almost exactly the same thing. It's just for poles, right? You've got z minus z naught to the negative m. Okay. And the proof of it is basically identical. So let me just do part of the proof because it really is identical, almost identical. So right, it's not at all exciting. Right? You say, well, look, if we're going in the reverse direction, say. Right, suppose you know that f looks like. You can just talk it through, right? Suppose you know that there's some analytic function that's analytic in a neighborhood of z naught, and it's non-zero at z naught, and you know that f looks like this, right? What does that tell you? That means that you have this power series expansion, right? Phi of z is going to have some power series expansion, some Taylor expansion, right? And that tells you that f is just going to be 1 over z minus z naught to the m times the above, right? Well, what does that tell you? That tells you that that f has a pole of order m at z naught, right? Just by definition. What does it mean to have a pole of order m at z naught? It means you have a Laurent expansion that starts at negative m, and there's nothing preceding the end, right? And so and then the other direction is basically the same sort of thing. Okay, so the proof is basically identical to the statement about zeros. It's basically just the reciprocal statement. And what you see from this statement is from this theorem is that in fact they basically are reciprocal conditions, right? So if we put the theorem about zeros together with the theorem about poles, what you see is the following. You can make a bunch of sort of trivial observations. So if f is analytic with a zero of order k at z naught, then 1 over f is a pole of order k at z naught. Right? Because having a zero of order k at z naught means that you are, right? Means that you look like, means that you look like this, right? Where this guy is non-zero at z naught, right? And then so what's 1 over f? Well, 1 over f is just going to be an analytic function, right? In some small neighborhood, it's going to be analytic because you know that the function is not going to be 0 in a small neighborhood, right? So it's 1 over phi is going to be analytic in a small neighborhood. So you have an analytic function times 1 over z minus z naught to the k. In other words, you have a pole, right? And then conversely, right? If f has a pole, if f has a pole of order k, of order k at z naught, then what am I going to say?
F has a 0 order k?
Almost, yeah. Yeah, that's what you like to say. But just to, you have to be a little bit careful and say the function. You actually have to define then this function, right? Because it's not defined. 1 over f isn't defined. 1 over f isn't defined at z naught, right? Because f has a pole there. Anyway, so in any case, it's basically as you say, right? This thing has a a 0 of order 20. So it's essentially true. Okay. And then there are a bunch of sort of more sort of straightforward observations that you can make. Right? If F and G have poles of order m and n at the same point, then the product has a pole of order m plus n, right? And you could say stuff about if these guys have poles of n and z, then f over g has, well, it sort of depends, right? It sort of depends, right? If m is bigger than n, you're going to have a pole. Right? If m is equal to n, you have a removable singularity. If m is less than n, then you have a 0. Right? So it's pretty obvious. Okay. Okay. So more of this sort of stuff is in proposition 3.3.4. Okay, so I'd like you to just please take a look at proposition 3.3.4 in your books. I'm just not to say that you don't all read every proposition in your books, but just to single out this one in particular. I hope you are reading books. I chose the book not because I wanted you not to read it, but because I hope you would read it. I'm not going to ask how many of you read your books, but I hope you actually read this book because, maybe you're all very comfortable reading mathematics, but I think it's a useful skill to be able to, set yourself down with a book and just read and get it. Okay, we have 10 minutes left, and I think that's enough to talk about essential singularities. So we are not going to do the greatest results about the behavior near essential singularities. Probably the greatest result is the great Picard theorem. There's also something called the little Picard theorem. What's that?
We talked about the little Picard.
Yeah. So I'll state the great Picard theorem, and just for your amusement, it occurred to me that this was Judy Grabner, the professor of math history at Princeton, at Pitzer, excuse me. Collects examples showing that English is not associative. Right, and I think this is a good example, right? Because it's not the great Picard. It's not the great Picard. It's not the theorem of great Picard or the theorem of little Picard, right? It's the little Picard theorem and the great Picard theorem. Right? There's not two guys, great Picard and little Picard. Right. Anyway, just for your entertainment. In any case, we're not going to prove either of those theorems today, although. If there's time near the end of the course, we could probably go for the little Picard theorem in a week or two. So, and I think it's pretty instructive to go after. So, but in any case, today we're going to talk only about the Casorati-Weierstrass, which says the following. Let Z0 be an essential singularity of F. given any W naught in C, given any neighborhood of W naught, and any punctured ball around any point around the singularity, and any punctured ball around the singularity, there exists a Z in the punctured neighborhood of Z naught such that f of Z lies inside of the epsilon of W naught. So the picture is this. You have your isolated singularity. Okay. You have your isolated singularity Z naught, and you're allowed to take any point in the plane, you're allowed to take any neighborhood of that point, and you're allowed to take any neighborhood of this point, and you're guaranteed that there'll be somebody in here that maps inside there. Right? So, in English, within any neighborhood of an essential singularity, f gets arbitrarily close to every complex number. Right? Right? No matter what complex number you choose, and no matter what neighborhood you choose here and here, there's going to be somebody in here that gets maps inside there. Okay. And that's not even, the great theorem. Not even the little theorem. Okay. So the proof is by contradiction. So suppose there exists some W in C, some epsilon neighborhood of W naught, and some punctured ball around Z naught, such that for all points in that punctured neighborhood, none of them are in the epsilon neighborhood of W naught. Suppose that this fails, right? So suppose that there is some W naught, and there is some neighborhood here, and there is some punctured neighborhood of Z naught, right? There's some punctured neighborhood of Z naught, so that for everybody in here, they all miss the neighborhood. Okay. Everybody in here maps outside the neighborhood. Okay. Nobody gets inside. Okay. So consider then the function g being 1 over f of z minus w naught. Right. F of z minus w naught is always greater than epsilon. Right? Because f of z, so on this punctured disk, right, on this neighborhood of z naught, epsilon is this distance is always greater than epsilon. Right? We miss this disk. Right? And so what does that tell you? Well, that tells you that g of z is smaller than 1 over epsilon, right? on that punctured disk. Right? Well, then, what does that tell you? That it's bounded there, and so what?
It's constant by the Descartes theorem?
No. No. Well, yes. Yes, get out. It's a removable singularity, right? Okay, so G can be defined at Z naught to make it so that it's kind of So now, we have 2 minutes, and we can actually do it. Observe. F of z is, by construction, 1 over g of z plus w naught. So let's consider F's behavior at z naught. So there are 2 possibilities. One is g of z naught is non-zero. Okay. Well, if in that case, f is bounded in some neighborhood of z naught, right? Because if g of z naught is non-zero, right, then we can in some small neighborhood we can bound it away from 0, right? We can bound it, away from 0, and so f is bounded, right? So 1 over, we can bound g away from 0, so 1 over g is bounded above, right? And so f is bounded in some neighborhood of z naught. But what does that say? That tells you that z naught is a removable singularity. Right? But it was an essential singularity, so that's not possible. The other possibility, where we're going for a contradiction, so this should also end with a contradiction. Let's suppose that g of z naught is 0, then then z naught is a 0 finite order. Right. If z naught were a 0 of infinite order, then there would be a neighborhood in which g is constantly equal to 0, and then your singularity would not be isolated. Okay, you remember it's an isolated singularity. So it's going to be a 0 of finite order. And so what does it give you? That gives you that z naught is then a pole of finite order. 0 finite order of g. So z naught is a pole of finite order of 1 over g, and thus of f. Okay, but that's also a contradiction. So either way you go, you end up with a contradiction, and so there is no, this is impossible. Okay, so that's it. Okay, I'm already past the time, but the statement of the great Picard theorem is here. And I might have actually misstated this as the little Picard theorem, but on any punctured neighborhood of an essential singularity, f of z takes on all boundaries in the complex plane, excluding perhaps at most. It takes on all values in the complex plane infinitely often.
Why?
Excluding at most one value.
I guess it was finite. You could put a ball. You pick the closest one and pick a ball smaller than that, and then you'd have a ball around it that didn't take on all.
Yeah, that's true.
And a little Picard theorem is for the entire, if the function's entire, if this property holds.
Yeah.
Okay. Yeah, I think you never stated it wrong. I think I was misapplying the little Picard theorem.
Okay. Okay. So yeah, maybe if there's interest, we will go after little Picard in the last week or so of class. Okay.